Okay, so we stop around this point of stability conditions. If you remember, we have two systems. Okay, we have two systems, and those two systems are in equilibrium. So we have E of A, and here we have also S of A, and here we have some B of A, all right, and even N of A. Okay, so this is system A, and it's in a contact with another system, okay, that have some energy B, S of B, yes, N of B. Questions? Yes? No? Right. Okay, so what we have made about the conclusions about the stability conditions. Stability conditions means that if you look on those two systems and they are in a contact, thermal contact with each other, and they are in an equilibrium, okay? This means that what we have shown, that T of A equals T of B, okay? So they have exactly the same temperatures, right? Also, they have exactly the same pressures. P of A equals P of B. Okay, this is system A, this is system B. Also, the chemical potentials of those two systems are exactly the same. Okay. Basically, any intensive parameters that we have in two systems have to be exactly the same in order for them to be in equilibrium. And we use this minimization of energy or maximization of entropy, basically the same property, in order to achieve those equalities. Those are the stability conditions. Right? This means that all the intensive parameters, all our generalized forces, are exactly the same in two systems. Okay? Now, so if we have a situation when two forces are exactly matching each other, right? So what this force means, this generalized force that we call temperature, that two systems are exactly the same temperatures, means that there is no flow of heat from one system to another. Okay? This equation, that there is this pressure of system A equals exactly to this pressure of system B, it means that the volumes are not going to change. There is no flow of volume from one system to another. They keep their volumes constant. The chemical energy, the chemical potential, what does it mean? That we have exactly the same two chemical potentials in both systems. Yes, and even more than that. There is no flow. So here there is no flow for T, there is no flow for for heat. For P, no flow of volume. Here, there is no flow of particles, electrons, whatever you call it. It does not mean that they exactly the same. You see, I haven't told you that EA equals to EB or SA equals to SB. I don't care about those extensive variables. The intensive variables has to be exactly the same parameters. So basically, stability equation tells us that there is no flow of anything in equilibrium. This is how we define equilibrium. Now, here we have proven this from the thermodynamical standpoint for macroscopical quantity. But if any one of you would like to or will go to an advanced class on statistical mechanics, we won't describe those conditions for microscopical world, but we go even further, and even for microscopical situation, we define equilibrium as a situation when nothing flows, even on the microscopical scale. Okay? So this is here we just use these conditions for macroscopics. For microscopics, there is something that is called detailed balance. Never mind. If any one of you will learn advanced statistical mechanics, you will hear this term. But what's important to understand and to remember those conditions, this is what they describe, but nothing flows. Okay, so all the systems that we say that they are in equilibrium, nothing flow inside the system and outside of the system. There is some sort of a balance that's going on. For example, a human being, you can consider me as a human being, okay, is not in equilibrium. Why I'm not in equilibrium? Yeah, no, I consume energy and I, get out of this energy out of my body somehow. Okay, damaged goods. So any flow of energy through anything, constant flow that is changing with time, is something that describes non-equilibrium system. Equilibrium systems defined, but nothing flows inside them, right? Okay, so this is nice. The other thing that we have heard, yeah, questions? No?
רגע, לי שאלה.
Yeah.
אתה אומר שום דבר לא זורם, זה כאילו לתוכן או בתוך עצמן?
It doesn't matter. It doesn't flow between system A and system B. Nothing flows.
לפנים לתוכן, לתוך עצמן?
Nothing flows.
או גם לתוכן בחוץ?
Nothing flows. Yes.
When you say that the system are stable, you mean that...
Okay, equilibrium.
Okay.
This is the difference. System can be stable, okay, but not in equilibrium. Right? So for example, I can have a wire, right? And inside this wire, there should be a constant flow of electricity, right? A constant current. Nothing really happens here. The current is constant, and you can say this is a stable system because nothing happens here. But the system is not in equilibrium because there is a flow of something that happens inside the system all the time.
So how do you define stability?
When this happens, when all the forces are exactly the same. All the internal intensive parameters in each part, no matter how small part of the system, is exactly the same. Okay, so basically, no. Stability conditions define equilibrium. In equilibrium, those guys persist. Okay, so let's if you have any kind of a system, right? And you take a very small part of it, but it's still macroscopic, right? I can tell you that the T and P and mu inside this larger part is exactly as the T and P and mu inside any small part. This is how I define equilibrium. Right? This answers your questions or?
No.
No, okay.
I don't understand what you're saying, that in equilibrium those intrinsic parameters are equal.
Yes.
But you also said that this is the stability condition.
Okay, so this is how they call it. And you're saying stable is, maybe this is what you're referring to, if I'm shifting something a little bit to the left or to the right, it should stay exactly at the same position.
No, you said that this is when you mean stable, it's not in equilibrium.
So there are so stability conditions in order for the system to be in equilibrium. This is how it's defined.
Okay.
So the stability conditions in order for the system to be in equilibrium. There are stable systems that are not in equilibrium, where those guys are not satisfied. Yes.
אם המחיצה הזו הייתה מקובעת, אז PA לא בהכרח היה שווה ל-PB ועדיין היינו מגיעים לבד.
But then they are not in equilibrium. So the question is if I would shift this guy somehow. You're asking what will happen if it was a non-equilibrium situation. If it was not an equilibrium situation, those conditions are not satisfied. In any equilibrium, that this has to be satisfied. All right. So, but this is what happens in equilibrium. What happens if I shift a little bit myself out of equilibrium, right? Now, do you remember when you were studying classical mechanics, right? Or even Newton mechanics, and you have this potential energy, and you have it as a function of x, right? Let's assume that this is a potential energy of a spring. Okay, I have a mass m, and I have a spring of constant k, and this is my position. So if I plot the potential energy, it's quadratic, very simple. Okay? So if you were taught properly, all the description of the system can be thought of, okay, so my mass is like a small particle, that is rolling up and down inside this ball, right? Stability means, okay, so this is the minimal energy, minimal potential energy. This system is stable. Why it's stable? If I push the small mass out of this stable situation a little bit to the right or a little bit to the left, it will go backwards, right? It will roll backwards exactly to the point from where I shifted it. Okay? So this is stable.
Because it's a bounded state, right?
Because it's a bounded, it does not matter, right? It's not about bounded state, it's about the property of the potential energy. Okay? Okay, now, if I would plot to you a potential energy that looks like this, it's also a bounded state, right? And I ask you, if I put my particle over here, this is U, this is X, and I put my particle over here, this is my potential energy. What will happen to this particle if I shift it a little bit to the right or shift it a little bit to the left? Yeah, it will run away and it will go either over here or either over there. It will never return exactly to the same point where it started. So this is non-stable. Now, what I need equilibrium or any equilibrium, I want it to be stable. What it means? It means that if I have a system with specific parameters and some small external or internal change occurs, I don't want my system to run away to some other state, to some other equilibrium state, right? I want my system to sit in this equilibrium. So it's not only enough to say, great, in equilibrium we do not have any flaws. It's also important to say something about if the system is stable, what does it mean? Internally, in terms of these parameters. So we know what are the parameters that define this minima, right? Minima or maxima. But it has to be more than that because we want a stable solution to our equations, a stable equilibrium. Which means if I change my energy a little bit, the system, where there is some fluctuation in the energy or in the volume, the system will gradually go back to this equilibrium position. Okay? This is why, in order to achieve stable solution, we started those tricks with the convex and concave function. So what happened to concave and convex function? So what we have shown that if we plot S as a function of our energy E, okay, the behavior of S has to be concave. Concave. Okay? Concave. Okay? Why do we need it to be concave? So what it basically means, right? This is what we achieved at the end of the class, that SU plus delta U plus S of U minus delta U smaller than 2S of U. Let's make it E, right? We're using E, so delta E, and delta E. So you see where I'm going. I established conditions for equilibrium. Now I'm going to perturb them a little bit. I'm asking what will happen to my system if I'll shift myself out of equilibrium a little bit. How my system should respond. Okay? This is why I'm going to some differences of the entropy with respect to energy. Now, how we achieve this? We basically made a claim. So if we have two systems which are exactly the same, S of E and S of E, okay, and we have another system with some small fluctuations, where here is S of E minus delta E, S of E plus delta E. Okay. The total entropy of this system should be larger than the total entropy of this system. This is how this condition of concavity appeared, right? Otherwise, okay, what was the claim? It was if it was convex, right, and the entropy of this system would be larger than the entropy of this system, what I would achieve? Would achieve that the entropy of the left-hand side will flow to the right-hand side. And this is something that I cannot obtain in equilibrium. Yep, because entropy is in the maximal state.
רגע, זה לא אומר 2 דלתה E, SE? 2 דלתה E?
2 SE.
דלתה E.
No. This is not a local claim. Okay, now, the thing about concavity, it is a global condition, right? It means that if I plot a chord, okay, from any 2 points, the sum of those 2 guys is always smaller than the actual value of the function. Okay, this is what concavity means. And this is a global condition. Okay, not local, global, but from this global condition, we can go over to a local condition, right? So let's write it, this guy, in the following form. So S of E plus delta E minus S of E minus S of E minus S of E minus delta E. And we know that this is smaller than 0. Okay. Now, let's divide both parts by delta E. Okay. So what we are getting over here? Derivative. The derivative, right? Okay, or if we will do it, so we have still 0 over here, greater than delta S to dE, at which point E plus delta E minus delta S to dE, at which point E minus delta E. Okay. Let's divide it another time by delta E. Okay. So on the left-hand side, we're getting 0. On the right-hand side, what we're getting, this is what?
Second derivative.
A second derivative. Okay. So this is d square s of dE squared. Okay. At what point? At the equilibrium. Okay? At the equilibrium. Exactly at the equilibrium. Okay? So you see, what are those delta E's? I shifted myself a little bit to the left, a little bit to the right from the equilibrium. E is the equilibrium. Okay? And it is actually very important in equilibrium. So you see, we have taken this, okay, think about the roadmap, right? We started with maximal entropy, we shifted entropy from one place to another, said it couldn't happen, obtained this global condition of concavity, right? And from this global condition of concavity, we are getting a local condition. Okay? This is a much softer claim, much softer condition than this one. This is local. And it means something about the derivative or the second derivative of this. Okay. Now, this is even further, right? Because you remember the stability conditions were about what? About intensive parameters. What is ds to dE? What is ds to dE? Temperature. Okay? So what we are getting here, dt to dE smaller than 0. Okay. ds to dE is temperature or 1 over temperature? 1 over temperature? 1 over temperature. Okay, so we're getting that d1 over t to dE is smaller than 0. Now I can make those claims. So what we're getting some derivative of what? Of an intensive parameter with respect to some extensive parameter energy. So this is not something very, very useful because we don't really know how to operate with entropies. Okay, so we need to do something else. Questions? No? Yes?
Can we open to change the derivative?
What do you want to change? The order of the derivative over here?
No, the d1 over c to dE, can we expand that to change and then
You can. You simply can. Now, if I'll do the following thing, and this is, don't do this in your lectures. If I'll ask you, if I have entropy, and instead of energy over here, I will put volume. Okay? I will put volume inside. Okay? Okay, what will happen if I put volume inside this?
It will change from
Okay, so can I still do the same analysis over here?
it's not קראו יותר, זה מאוד כמות.
Entropy is still maximal equilibrium.
So entropy is still maximal, but instead of S plus delta E, I will have V plus delta V, V minus delta V,
SV.
SV. And I can still make this claim, all the claims that I have done, but instead of treating this as entropy as a function of energy, I can make it as of entropy function of volume. Okay, so I can repeat all this algorithm for any extensive parameter. Why? Because as you said, entropy has to be maximal. And all of this, what I have tried to explain you over here, is a consequence of what? Of a maximal entropy. But again, is it nice to work with entropy? No, right? This is why we use energy and we use free energy and we use all those different stuff. We don't like entropy because we don't really have a natural understanding or intuition about it. So instead of looking on entropy, let's look on what? An energy. Okay? Yes, question.
אני מסכים שהתיאוריה צריכה להיות מקסימלית, אבל כשאנחנו עובדים נפח, כשאנחנו משנים את הנפח באיזושהי צורה, זה לא בצורה של מינוס PDV, זאת אומרת שאם אני...
No. Again, you have to repeat what I've done last week. Internal changes. It's all about internal changes. But let us see, I will do exactly this for energy and entropy, and you will see the claim again. Okay, so what I know about energy. So entropy, it has to be maximal. What energy has to be? Minimal. Okay, so if we had a concave function for entropy as a function of energy, the energy as a function of entropy will be convex, right? So it will look something like this. Now, I can do this trick once again, right? Okay, so convex function.
Stas, this would be because minimal energy?
Exactly. Okay? So if I will have E of S and another E of S, right? This is the claim. And I will perform this trick of looking of ES plus minus plus delta S minus and E of S plus delta S. How I achieve this? Some internal changes in order to answer your question. Okay. Now, where the energy, so this is S. This is S minus delta S. This is S plus delta S. and here are 4. So how was our claim going? We said, look, if those two guys, okay, this is the total energy, this is the energy here, is 2E of S. And the energy over here, because energy is extensive, right? It is ES of minus delta S plus E of S plus delta S. Right? Now, who is greater? This guy on the left-hand side or this guy on the right-hand side?
Right.
The left-hand side.
Then it is minimal.
Who is greater? You're right. Who is greater?
Money.
Right.
Who is greater? Yes, yes. The right-hand side is greater. Why? Because this is computed at equilibrium. So energy is minimal, right? So this is the condition that always has to be satisfied. And this condition is exactly the convex property of the function. Okay? Now we go and we perform this trick once again, right? We erase all of this.
It's exactly the same, but
It's exactly the same. Okay? It's exactly the same. We have that 0 is greater, 0 is smaller than ES plus delta S minus E of S plus E of S minus E of S minus delta S. We perform exactly the same. We divide it by delta S once, we obtain the derivatives, we divide it by delta S another time, we obtain the second derivative, and we obtain here that d squared here minus, yes, thank you, ds squared is greater than 0. Okay? So we obtain the same condition. Okay, so E is a convex function, not concave. This is a global condition, and this is a local condition, and again in equilibrium. Nice. What's so nice about it? It's again, right, so beforehand I had entropy and energy, right? And here I have energy and entropy. I don't really want this entropy over here. Oh. Okay. Maybe I can do this in a little bit different fashion. Okay. Energy is minimal. It's always minimal. So if I'll have here, instead of S, I will have V. Okay. And I have V. And I have V. The same argument holds, right? I have V. I have V over here. I have V over here. Plus delta V. V minus delta V. And again, the same argument holds. V minus delta V. V plus delta V. What it will bring to me? It will bring to me that dE squared to dV squared is greater than 0. Let's take another trick. What if I had here n? Right? It's another extensive variables. The only thing that I need, right, in order to make this argument valid is that here or here, this is V, stands an extensive variable. Right? If here stands an extensive variable, the only thing that I need to do is erase the previous value that I have over here, write down this extensive variable, and repeat my argument. Right? So if I had n, I would obtain d squared e to dn squared greater than 0.
You can do it so it's what?
As long as my variable is extensive. Okay? As long as my variable is extensive, I can always perform this trick.
אנרגיה של תת מערכת פה היא נחשבת מאפיין של מקרוסקופי או מיקרוסקופי?
It's always macroscopic. We are in thermodynamics, everything here is macroscopic.
גם של תת מערכת מבחינת כל
Everything is microscopical. Everything. Think about it. Thermodynamics, the 19th century science. They have ideas about what atoms are, but atoms were discovered and properly proven only in 1907. So, right? Okay, so, but again, what do we want to show? Why we use this? Okay? I haven't done it in order to torture you. I've done it in order to perform to you what real stability conditions are. Okay? So we can tell this that this is d of ds of d over ds, right? Which is dt over ds, right? And this is greater than 0. And the same goes over here. D over dv of dE over dv equals to d to dv of minus p. This is greater than 0. And here it is d to dn of dE to dn, which is d to dn of mu. And this is greater than 0. It's not an initial condition. It's a stability condition. Real stability condition. So the quality of the intensive variables, that's what defines the equilibrium. Where the equilibrium point is. Those guys define to you that even if you move a little bit from equilibrium to the left-hand side or to the right-hand side, this is why you will return to your equilibrium point. This is why it's either minima in energy or maxima in entropy. Yes?
You said that all of this, like the equation like E to S plus delta S, this is a global property of the function.
Because of convex.
Yeah.
Yes.
So why are all the equations true only in equilibrium and not for...
Because my argument about about the maximality of entropy or minimality of energy holds only in equilibrium.
So the convection function is a global property,
But measured in equilibrium.
Okay.
Okay? So you have to measure it in equilibrium. What do I mean measure it in equilibrium? You do something to the system, you leave it alone for a year or two, then come back and look at it, and then you say, oh, it's now in equilibrium. It does not work for all the systems. It works for 99% of the systems. It does not work for glasses, for example, or any glasses systems. Yes?
התנאים האלו שקולים לתנאים שראינו בהתחלה?
No. So the question is, are those exactly the same conditions, okay, that we've seen about TA equals to TB, and mu A equals to mu B, and what PA equals to PB? No. Those are complementary conditions. Those conditions define equilibrium. Those conditions define why you're not going to move spontaneously out of equilibrium. Yes. The stability. Yes. Exactly. So all the physical systems that can reach equilibrium, they have to satisfy this. No. So again, in all of this class, we assume that the system is already in equilibrium. If it's somehow kicked out a little bit, not too strongly, right? It's kicked out a little bit, it will return to this equilibrium because those conditions have to be satisfied. I don't know. What will I know that if you started from non-equilibrium situation, you will reach to some equilibrium situation. I don't know how, I don't know when, I know that you will reach that. That's all that I know. No. This is all what happens to you in equilibrium or in the vicinity of equilibrium. It does not tell you anything about what happens to you out of equilibrium. I don't know. Nobody really knows. Questions?
What is vicinity?
What?
You said this happens in equilibrium or in vicinity or something?
Vicinity of equilibrium. Closer environment.
In a neighborhood of.
In a neighborhood of equilibrium.
אמרת שצריך לפרמטרים אקסטנסיביים.
Yes.
אקסטנסיבי, רק שני הצירים צריכים להיות אקסטנסיביים, או רק אחד צריך להיות אקסטנסיבי?
So both of them have to be extensive. Both of them have to be extensive.
וכשישתיהם אקסטנסיביים אני יכול לעבוד עם עקומה בעצם שהיא כמורה?
Yes.
אם לא שתיהם אקסטנסיביים הייתי עובד עם...
אתה חוזר על עצמך.
כן, פשוט רואה כבר.
Any other questions?
אפשר רק שאלה נוספת?
Yes.
אז בעצם כל מצבי שיווי המשקל הם יציבים? כי הרי לא
Yes,
עשינו הנחה אחרת.
we assume, okay, so the question is, are all equilibrium states stable? And the answer is no. But what we assume is that they are, it's interesting. So our assumption about an equilibrium says that equilibrium must be stable. This is how we define it, okay? Any macroscopical system in equilibrium, it has to be stable. This is how equilibrium defined. But there are situations when it looks to you like the system is in equilibrium, but it's really not. In any physical equilibrium system, this has to be satisfied. When this is not satisfied, the system is out of equilibrium.
תודה.
Yes.
The derivatives have to be other variables constant.
Yes. 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 So the general claim is when I have phi intensive variable okay, and let's call it I extensive variable conjugated to I, what we see is d phi to di has to be
itself?
conjugated to I, to phi.
Phi, yeah.
Yeah, thanks. Okay. This has to be satisfied. Okay. This is what we see. Look on those expressions. So P is intensive variable, it's conjugated to entropy. P is a conjugated, minus P is an intensive variable conjugated to volume. Mu is an intensive variable conjugated to the number of moles or the number of molecules. And this is always satisfied. How to prove it? Well, we extend the treatment that we had over here to any extensive variable that the energy depends upon, and use again this trick. And this is the general stability conditions. Everything here is under condition, is under assumption that we are in equilibrium. All that we are going to do in this class is about equilibrium. Okay? Don't you worry. Yes.
Those are general sentences or just in equilibrium?
Just in equilibrium.
When we go from a non-equilibrium state to an equilibrium
I don't
state?
know. Depends on how far your other equilibrium is. I really don't know. There is no general theory about what happens out of equilibrium. There is very general theory about what happens in equilibrium. Okay. Yes.
סטס, רשמת שכאילו הדופיל לדו-I גדול שווה מ-0,
Yes.
בכל כאילו, בכל מצב, אבל יש לך פה מינוס דופיל לדו-I.
Oh, because what is, so the question is, right, I'm writing here, it's always greater than 0, but I have this condition over here. It has a minus, right? So dp to dv is smaller than 0. Why is that? Because the variable is minus p. Okay, so think about it as written minus p dv greater than 0, right? The variable is minus p, is not p itself. Yes.
conjugated זה אומר המשתנה של?
המצומד.
יש שאלה.
No, we have to. Quick question.
כן.
Quick.
איך אני יודע בעצם מה הפרמטר המצוין שלי כל פעם?
Oh, this is the Legendre transformation that we have, right? If you write this down, if you write down dE, right? dE is, for example, TdS. T is intensive, S is a conjugated extensive. Minus P dV, intensive, extensive. Plus mu dN, intensive, conjugated extensive. Okay?
ול-E יש איזשהו גודל...
That's the only thing that I know. Then E is extensive. This is first lecture. Okay, so where it brings me. Now everything, if you think about it, my strategy over here is to describe to you thermodynamics as some sort of analysis class, right? We have functions, those functions have properties, we can take derivative out of them, the first derivative, the second derivative, everything is continuous. Now, this is based on how this field was viewed in the 19th century. That we have a material, and the material is continuous, right? So whatever we do to the material, we think about gases, right? This is all originated from gases. We push on the gas a little bit, it slowly compresses, slowly heats, right? So everything is somehow performing a continuous transformation from one state to another. This is why all of this is very nice and continuous properties of the function and continuous derivatives, blah, blah, blah. But what happens in reality? Is everything continuous? No. This is maybe the problem, but the one simple assumption that we maybe missed. So, is the behavior in nature continuous? Right? So somebody already told me that no. And the nicest example is what happens if we have a bucket of oil, a bucket of water. Okay? So water is a liquid, right? And we know that when we will start to heat this water, we will obtain some vapor that is coming out of this water. Right? This is vapor. And if we will continue this process, eventually, what will happen? A fire, right? Why? Because all the water will evaporate, we will be left with the bucket, and the bucket will heat up and explode or do something different and not nice in our kitchen. So we know in the process that whatever was water, okay, so it's a liquid, had been transformed into a gas. Okay. Now we can turn off the fire, we can put the water inside the refrigerator. This is my refrigerator, and we'll get ice. Right? Now we can say, well, Stas, you can shift your system from liquid to gas and from liquid to solid by some specific continuous transformations. Right? You heat it a little bit, vaporizes. You cool it a little bit, it's isolated. Questions? This is all what we familiar with this phenomenon. Right. But if we look closely, the process is a little bit different and a little bit uncontinuous. Right? So what I want to look closely. I want to look on this process when I heat my water. Okay, so let's assume that you have a kettle and you heat the water. How the water is heated inside. Okay, so first of all, if you try to heat with our kettle the water in outer space, will it work? Why not?
No oxygen.
No. Gravity, right? Outer space gravity. So what happens is I heat over here. Okay, so the water becomes hot in this small area, right? How couldn't it be that everything is hot over here, right, and cold over there? So what happens is that the hot water is actually going up, and the cold water is going down. Okay, so we have a natural mixing because of gravity. Right? Hot water becomes a little bit lighter, and cold water a little bit denser, lighter, denser. Okay, so this is the mixing that we have. Hot going up, cold going down, and eventually almost all the water in our kettle or in our bucket is approximately with the same temperature. Very nice, but if we look closely enough when we produce this process of hot going up, cold going down, at some point we start to see that it's not only water that is going up. What we start to see is small bubbles that are transforming in the vicinity of this area, and those bubbles are going up. Okay, so we had water, and out of nowhere, you just look on it, and out of nowhere, it's not that the metal here is transformed into bubbles. It's the water that near the very hot metal are transformed into bubbles. Something really abrupt happened in this process of heating. Okay? So the process is not continuous, small changes of the water. At some point, okay, when this metal is hot enough and this transformation hot up, cold down, hot up, cold down, eventually we start to see bubbles. And even more, those bubbles are becoming larger and larger and larger, and if you have seen boiling water in a kettle, those bubbles are enormous, right? Huge. By the way, do you know a technique how I can measure the temperature without having a thermometer? The size of the bubbles. The size of the bubbles increases as you getting closer and closer to the boiling temperature. It's a very known technique, I think, in China. In order to brew tea, you need to around 70 Celsius, 70 in order to brew tea. You don't need 100, 70 or 80. How you know that it's 70 Celsius over there? Approximately by the size of the bubble. Okay, so for our purposes, we look on this abrupt change, and we know that something extreme happened. Right? It's not a continuous transition of small water into gas. It's a portion of water stopped being water, right? Abruptly. Now, we see those behaviors in many different physical systems. For example, we have something that is called, this is temperature, paramagnetic systems. What is a paramagnetic system? Paramagnetic system is when I measure magnetization, okay? It has no magnetization. This marker has no magnetization. The net magnetization of this marker is 0. But we have systems that is paramagnetic for high temperatures, and as we decrease the temperature, at some point, it becomes ferromagnetic. Okay, what it means ferromagnetic? A spontaneous magnetization. Out of nowhere, the system became a magnet. We haven't done anything. We haven't applied any external field, nothing. Right? We just changed the temperature a little bit, and out of nowhere, the system became magnetic. There are systems, okay, if you look on them as a function of temperature, and this is resistivity, or resistance. Okay. And we look on this resistance as a function of temperature. Okay, so we know it has to decrease, or resistance is growth with temperature. But we cross a specific point Tc, and the resistance simply drops to 0. Okay. This happens in what systems? Superconductors. Right. So this is ferromagnetic paramagnetic transition. This is a transition from conducting, regular conducting state to superconducting state. And in some systems, not all of them, this transition occurs abruptly and not in continuous fashion. Okay. And there are other examples. There are examples of insulator-conductor transition. There is a transition even for models of how human beings vote, right? It's not a physical system, it's something much, much more complicated. But there are, we know, examples, many examples, that the changes are abrupt, extremely abrupt. So how can we explain or describe those abrupt systems or abrupt changes when we use our thermodynamical, extremely continuous description of everything, right? We now have energy and it's continuous, we have entropies and continuous, we have global properties about convex or concave, we have local properties about the second derivatives. Everything is nice, but how can we describe, and this actually happens in nature, it's not something that I invented over here or mathematical description, how we can describe this with the formalism of thermodynamics? What? No! So it was before delta Dirac delta function,
מדרגה.
or even less. Some functions can be continuous, right? But their derivative can jump. So my assumption about the function is continuous. Function can be continuous, but it does not say that its derivative is a continuous function as well. So we have to limit ourselves in our description of thermodynamics to functions that can actually have abrupt changes, right? So what I'm going to try and introduce now is what happens to a function or thermodynamical description when we assume that there has to be some sort of an abrupt change to the system. And where I'm going is phase transitions. Phase transitions in thermodynamics. This is the topic. All of what I described you over here, this transition from one state to another, this is phase transition. This is a liquid phase. This is a gaseous state phase. This is a solid phase. All of phase transitions that we know of, except some very specific and extraordinary points, are abrupt. So we are going to describe phase transitions.
We can say that context and concave functions are not.
We assumed a lot of things. You're right, we can say. The thing is, we have to look on the nature and not assume something or tell the nature what to do. We have to take from the nature its behavior and introduce it in our mathematical formalism. Okay. Now, do you remember this equation that I derived in the first lecture, which was S dt minus V dp? There's huge number of different relations in thermodynamics. It's always complicated to know what to use. Okay, so we're using this equation, plus n d mu. It had a name.
That's the F.
What df? That's not exactly df. Gibbs Duhem. N d mu, not mu dn. This is, if it was mu dn, it was not equal to 0. It was equal to Helmholtz free energy. With the minus over here. So this is a relation that we derived. Okay. Now, let's play with this a little bit. In thermodynamics, you're always playing with something and hoping for the best. So n d mu equals to minus s dt plus v dp. Okay. Make it big S, big V, big V, big S.
Why did it equal to 0?
Why it equals to 0? Well, you go to the first lecture and I played on the board a little bit and we obtained this equation. Okay. If you remember, I've used the Euler property about homogeneous functions, and then I introduced it into some differential, and this is what we get out. Okay, so we have d mu equals to minus s dt plus v dp. Okay, so why I put big S and small s over here? So small s is big S divided by n, and small v is big V divided by n. So basically, this is the total entropy, and this is the total volume, and this is total number of particles, so the number of moles. Okay? So small s is entropy per particle, and small v is volume per particle. Okay. Now, from this, guys, what I obtained two equations. First of all, this is a differential. So minus s is d mu to dt. So d mu to dt equals minus s. Okay? And d mu to dp equals v. dt equals v. Why I'm using mu, my chemical potential? Remember that in equilibrium, mu has to be exactly the same. So if I'm looking on the system, that here I have water, and here I have vapor. And those two guys are in equilibrium. Exactly in equilibrium. Remember, whatever I'm treating over here, I'm treating only equilibrium problems. I cannot do anything or say anything about what's going on in out of equilibrium. So assume that my system is separated into two systems. One is water, one is vapor. And this system is in equilibrium. The total system of water plus vapor. There is separation between vapor and water. Okay. But what can I say? That mu over here, let's call it mu water. And here I have mu of what? Mu of vapor. Because those two systems are in equilibrium, what has to be the case? It has to be that mu water equals to mu vapor. This is the continuity assumption. Everything is continuous. This is what we obtain from equilibrium. Right? But equilibrium does not tell us how this mu is going to change as a function not of an intensive parameters, but of an extensive parameters. Right? Maybe if we change the intensive parameters and not extensive, there should be something different. So what I'm trying to say is we can assume the following thing. If this is t, and this is p, and this is mu, right? Because look on this. Mu is a function of t and p, right? So it's like a manifold, two-dimensional manifold that depends on this parameters. Okay, so let's assume that it goes like this. And this is my two-dimensional sheet that describes the behavior of mu. So here is the description of water. Okay. Here something happens. Okay. Here something happens. And I can say, well, it's not continuously growing up. There is another two-dimensional description of vapor. So the stability conditions that we derive, they only say that mu is continuous. So if I'm going from water and I'm crossing to vapor, right? This is the situation exactly at the border. So here my whole system is water. Here my whole system is vapor. Here I on the verge of going from water to vapor over here. Okay? Because the system is in equilibrium and I'm treating only equilibrium, when I'm located over here, mu of water have to be mu of vapor. This is correct, right? But my stability equations haven't told me anything about the behavior of mu with this intensive parameters, right? So there could be one derivative on this side and another derivative of mu on the other side. And it can perform a jump. Okay? So the abrupt behavior of phase transitions that we have seen before, we are going to translate to what? We're going to translate that S of water is not equal to S of vapor. And V of vapor does not equal to V of water. So at the moment of phase transitions, those interesting situations, when the system abruptly changed from one behavior to another behavior, we can say there is a jump. Okay? There is a jump. Like in any function, the function does not have to be. Okay? Because this is mu, as this is a function of v. So mu can grow, but it has to change its behavior at some specific point. The function itself is continuous. Its derivatives, they are not continuous. And what we see exactly, for example, in this transition from water to vapor, from water to gas, when we heat the system, what happens? think about the small molecules. So what are those bubbles? Okay, so we know that the water is composed out of molecules. So those molecules haven't disappeared. They haven't stayed in the bucket. They transform their behavior from something that looks like water to something that looks like vapor. What happens on a micro scale? What happens per particle? We do see that the volume per particle is jumping from something extremely small to something much, much, much larger. Okay. And this is a discontinuous transition from, let's think of me as I am a particle in the water, and I'm moving a little bit, and I have a specific volume. What will happen as a function of heating, at some point I will abruptly perform a extremely large dance, vial dance. And because of this big movements of myself, I'm going to have a much larger volume, self-volume. And this is what happens at phase transitions. Specific quantities like entropy, like volume, okay, which are extensive, but per particle they are performing a huge jump from one value to another. And this has to be part of our description of what's going on in the real life system. Okay? We cannot simply assume that everything is simply continuous. The functions, like chemical potentials, they have to be continuous because the system has to be in equilibrium. But different derivatives, they already can perform specific jumps.
So you're saying that the intensive parameter has to be continuous, but the extensive parameters don't have to be.
So these derivatives, the derivatives of the intensive parameters with respect to extensive parameters can perform a jump.
רגע, ליאון.
Yes.
אתה בעצם אומר שכל המערכת הזאת נמצאת בשיווי משקל של הגז ושל הנוזל, אבל
Exactly.
בכל זאת, למרות שהיא בשיווי משקל, אבל מה בשיווי משקל שצריך שכל הגדלים...
Yes, all the intensive variables are exactly the same. The pressure of the water and the pressure of the volume are the same. The temperature of the water and the temperature of the vapor is exactly the same. All the intensive parameters are exactly equal, but their derivatives are not. Right?
Okay.
This is important to know. This is somehow needs to be part of our behavior.
ולמה רק סימנו את החלק האדום הזה?
This is the transition. This is the transition.
מה אמרנו בהקשר אליו?
This is a transition like this. This function or this system lives on this red line.
זאת אומרת, זה איפה שזה בעצם קופץ, ואין שבאמת חלק.
Yes.
ובעצם אמרת שבשני
אתה חוזר על זה.
האקסטנצים זה רק משהו אחר.
This graph is V to mu and they are both extensive.
Sorry, again?
This graph,
Yes.
it's mu to V and they are both extensive.
Yeah, mu is extensive? Mu is not extensive.
No.
Okay? Mu is not extensive.
So intensive to another intensive can be also done.
We don't know. Yes. Basically, the derivatives of intensive parameters can perform a jump. This is what we need to assume.
But extensive to another extensive is always continuous.
That, yeah. Okay, so if we look on an Pn of t, right? And we want to describe this line. This line, okay, this line is termed coexistence line. Why coexistence? When for specific values of p and specific values of t, mu is exactly the same, but we have a system that is composed both of vapor and both of water. Okay. So basically, if you look on p as a function of t, we have phase A and phase B. In our case, it's going to be water and vapor. And this is our coexistence line.
מה זה coexistence בעברית?
Coexistence. Do you.
רגע, אבל למה אנחנו קוראים
Something
לזה
that we don't have in Israel.
אז למה אנחנו קוראים לזה רציפות? זה פשוט, האינטנסיבים פשוט שווים והאינטנסיבים פשוט עושים, אבל
Because mu is continuous. Mu is simply
זה
continuous.
פשוט גודל קבוע לשניהם.
Mu is continuous. Mu has to be continuous. This is our part of our conditions.
אבל הם וייפר לא צריך לחשוב עליהם מיו ווטר במצב של שיווי משקל.
Yes, this is why it's continuous. This is exactly why it's continuous. Now, we can have, if you think about it, how we obtain this guy. We obtain that mu of A of T and P was equal to mu of B of T and P. So we have one single equation in order to describe what is this coexistent line, right? How do we know that it's a line and not that something that looks like this, right? Why it's not an area? Coexistence area. Why not?
אבל אחרת,
כי מה קורה?
אחרת אתה צריך תמיד להיות באחד המצבים.
Why not? There is a coexistence area. There is a
פיוז מקטין לך את הממד.
yes, right? So think about it. This exactly. So this is one equation that we have, and this equation defines us the conditions between T and P, okay? Between T and P, and from dimensionality, T has to depend on P, and this is simply a line. That's it. We have one equation, and that's it. We have a two-dimensional space, and we have one constraint. So the dimensionality of whatever comes out of this has to be one-dimensional. So this is why it's called coexistence line and not coexistence area.
רגע, אין לנו שלושה ממדים, מיו, T ו-P.
Oh, if you have some other intensive variables, it's going to be maybe an area. Yes. Yes.
Explaining why this is a line and not an area.
Of dimensionality. The dimensionality of the dependence between T and P have to be one-dimensional. And that's it. This is a dimensionality constraint. Okay, but what happens if I have face A and face B and face C? What will happen then? Okay, so we have a triple point. Triple point. Why it has to be a point and not a line? Why don't we have it? Right? Two constraints. Two constraints from two dimensions to zero dimension, and zero dimension is only a point. You can have several points, yes, but they have to be points. We can extend it to much more many variables, P and T and etc. etc. But there are always those dimensionality. We have such and such amount of equations, coexistence of mu's. We have such and such constraints, and this is why we will get a line, an area, hypercube. It's not really so interesting. For our case, right, we only interested. We have some specific phase A. We have some specific phase B, and we have a line. How can we define this line? How can we maybe find it or write an equation for this line? Equation for coexistence.
What is this chemical energy? It's the derivative of the energy with respect to
mu is dE to dN. Is how your energy is going to change with respect to the amount of particles.
So you you need the energy in each state, and you just plug stuff in, right?
Okay.
Isn't that? And then just yes.
The question is?
Isn't the question? Isn't that how you do it?
Yeah, this is how you do it. This is how I've done it, right?
So I assume that's how you find it.
Yeah. So no. But why this condition came from? From the stability relations. Remember in the beginning of the class? Okay, mu A equals to mu B. The vapor and water coexist together, and they are in equilibrium. This is why I can write that mu A equals to mu B. Otherwise, I don't know what the relation between the chemical potentials of two systems are. Only when they are in equilibrium I can say something like this. Otherwise, I can't. Okay. So equation for coexistence. It has a specific name. It has a specific name, and it's called Clausius-Clapeyron. Okay, so how do we find it? This is P, this is D, and this is our equation. let's look on this small shift. Assume this is a small shift. I'm going from one position to another position on this coexistence line.
מה אנחנו מנסים לעשות?
I want to find, so I've proven to you this coexistence line is simply a line. How you find it? Okay. So basically you want to find where the phase transition occurs. In order to find where the phase transition occurs, you need to find, okay, so this is phase, this is vapor, this is water. Where I'm crossing from vapor to water is when I'm crossing this line. Right?
הקו לא פשוט מוגדר לפי המשוואה?
How you find it?
אוקיי.
Okay. How you find it? So you can solve it. If you know the potential, chemical potential, you can simply solve it, right, and obtain it. But if you don't know how to solve it, there is an alternative way, and this is what we are trying to show. Okay, so we know that mu A over here and mu B over here, they are exactly the same. Right? So mu A of T and P equals to mu B of T and P. This means that d mu A of T and P equals to d mu B of T and P. So basically I'm moving, this was my mu over here, and I shifted myself along this coexistence line from one position to another. Okay, so what is this d mu? We know this is minus s a dt plus v a dt dp equals to minus s b dt plus v of b dp. Alright, so let's shift everything to all the dp's to the right hand side, all the t's to the left hand side. So what we're getting over here, we're getting s of b minus s of a dt equals to v of b minus v of a dp. And out of this equation, we obtain that dp to dt, right? This is not a solution of this function already. I don't really care, right? I want some differential equation that will define me a line. This is what differential equations are for. So dp to dt equals to sb minus sa divided by vb minus VA. And this is Clausius-Clapeyron equation. So if we want to define, or if we want to know something about the phase transition and how to find this phase transition, right? Two ways. One way, as you said, if you know the chemical potential, solve this equation, and you know then how T P is defined as a function of T, or T how it's defined as a function of P. The other way around, this is what Clausius and Clapeyron suggested, is, well, you have this relation. The only thing that you need to know is by how much your entropy, so when you're crossing, I obtain this equation when I follow this line. What are those differences? SB minus SA and VB minus VA. When I'm crossing this line, right, this coexistence line, I know there has to be jump. What jump? There has to be jump in entropies, and there has to be jump in the volumes. Those guys are discontinuous. This is what we shown. If it was continuous, we don't really know what this right-hand side of this equation equals to. But we do know that when we cross coexistence, when we go from one phase to another, there is a jump in entropy and there is a jump in volume, and those jumps, exactly those jumps, they are what define when this phase transition occurs and how it occurs. Yes?
יש הבדל במה שסרטט, כאילו מעבר מ-A ל-B או B ל-A?
No, so you don't really care because you want a differential equation The question is there is a difference from going from this guy to here or that guy to there? You don't care, because if you multiply this by a minus and this guy by a minus, they cancel out. Okay? The only thing that you need is a differential equation of p as a function of t. And here you got it.
קוראים לדבר הזה קלאוסיס קליי פירון?
קלאי פירון, כן. Yes.
אני לא מבינה, אם אתה הולך דרך הקו של ה-phase transition, למה יש לך קפיצה אם אתה על הקו עצמו?
So in order to derive this, I followed the line. But what are those differences, SB minus SA and VB minus VA? Those are these values of entropy and volume on this left-hand side and the right-hand side. And they have to be jumped for them.
וכמה קוראים לשיטה הזו? קלאוסיס קליי פירון?
This equation is named after two guys, Clausius and Clapeyron.
Okay, so...
Yes.
But if entropy and volume are discontinuous, doesn't the derivative come out to be continuous?
But you don't care. Look what I'm defining to you. I'm not defining to you how the system is going to change when I'm going from here to here. I'm describing to you what is the function that describes this line. It's a different question. All right? So S is going to jump. V is going to jump. Yes. But where it's going to jump? Is it going to jump over here? Over there? I know that it's going to jump along this line.
אפשר להגיד שזה יוצא גודל שהוא רציף, והדבר הזה פה מישהו שדרור בגודל...
This line is continuous, yes. This we know.
זאת אומרת, לאורך הקו הזה רציף בעצם, זה מה שאתה...
Yes.
ואנחנו יודעים שהגודל הזה, שהשיפוע שקיבלנו פה זה גם גודל רציף, כי זה משנה אינטנסיבי.
You don't need it. You're going into the wrong direction. You don't need about any extensive or intensive properties of this one. You don't care. Because they are both intensive. Okay. So what we actually will see when we treat a system, what we will see, what those jumps means. Right. So if we plot volume as a function of pressure, right? As a function of pressure, what do I expect? How this function will behave, generally, how this function will behave. How V will depend on V. V on P. So what we have proven? We have proven that D minus P to dV, okay? גדול שווה מאפס. Okay? This is what we have proven. So V is decreasing as a function of P. Okay? This our expectation for any system, right? But what if we have a phase transition? So this is no phase transition. Nothing really happens over here. This is no phase transition. Let's assume that it happens at temperature T equals T1. Okay. I increase my temperature or I decrease my temperature. The only thing that I know that V always have to decrease with P. Okay. How I describe a phase transition. I know that I will reach a specific point where I have to perform a jump in my volume. Okay. This is water becoming vapor, bubbles occur, the volume of the bubble are much higher. Okay. So there is some specific delta V, but it happens at a specific P. And this P over here is exactly the same. Okay. This is temperature. Always what we put here on this board is for equilibrium. Everything. Okay, cool. Everything that is plotted, said over here is for equilibrium only. Everything. Okay, so what do we see? For specific temperatures, there are no phase transitions. What it means, I'm staying all the time exactly at one phase. I'm shifting my P, okay? For example, I was at specific temperature over here, and I have shifted my P to the left or to the right, and I'm still at phase B. Right? But there are temperatures, I'm shifting my P up or down, and I'm still in phase B. But there are some specific temperatures. This is T1. Here I have T2. Right? And I know when I'm going for T2 and I'm increasing my P, at some point I have to cross this phase coexistent line. What happens at coexistent line? Volume drops down. Okay? So what we have is a specific jump at our volume. Now, in order to describe any system, we need to assume something about what happens to those volumes. Now, you already have learned about gases, and you have learned that there is a thing called ideal gas, right? Can we have a phase transition for ideal gas? Is there a phase transition for ideal gas? So instead of plotting V as a function of P, we plot P as a function of V. By the way, why I'm using P and V and not P and T or V and T or V of S? Why use P and V?
Conjugate variable?
Yes, and because I know that this relation has to be satisfied. This relation tells me something about the general behavior of the function. If it was P and T, they are not, as you said, conjugated variables, and I don't care. I don't know what they are, how they behave. When those variables are conjugated, there are those conditions, stability conditions. Okay.
אבל הם לא נכונים, הקשר הזה רק להשיג נקודתיות במשחק שם?
This? But every point here is an equilibrium. Everything that I plot is an equilibrium. Every point over here is an equilibrium.
So the process is very slow, like quasi-static?
I'm doing something, I'm waiting, and then I'm looking on my system and then I measure.
לפי ההיגיון שלי, כאילו, כשמשהו בשינוי משקל, אז הנפח לא מוגן.
Okay, so again, so the question is what actually happens here? How I jump? We'll see in a second. Okay, so P and V, right? What is the ideal gas equation? nRT. And here is the number of moles. R is the gas constant, T is the temperature, P is the pressure, V is the volume. So from this equation, I know that P equals nRT divided by V. How those equations look like?
Like this.
They just decay, right? Doesn't really matter what T is, they decay like this.
So for a constant temperature, there's no jump?
Exactly. So if you look on the ideal gas, this is T1, this is T2, this is T3. P is always a continuous function, a decreasing function, right? This guy is satisfied. P is a decreasing function of V, but there are no jumps in ideal gas. There is no phase transition. Right? There is no phase transition whatsoever. This is why it was a bad model. Why it's bad? It's very nice. You can compute, and we will use this model a lot in this class, or the ideology of this model, but it's not giving you anything interesting about the system. Okay? The system cannot show any phase transitions. There are no abrupt changes. Now, we do know that when we heat water or we cool gas, there are abrupt changes. This is something that we look on experiment and we see it. So this is why ideal gas is a bad model.
What do we see in the experiment that's discontinuous?
What will happen to a vapor when we cool it down?
It turns into water.
Yes, spontaneously and like that. Okay? You cross the temperature and then you cool it down a little bit, and whoop, all the water or all the vapor is turned into water at once. Yes. Yeah? Yes.
מה הגרפים של T1, T2, T3
So you put here T1 and you look on the plot, it goes like this. This equation is in equilibrium. How you derive this? Right? You use the quasi-static process, you had a pulley, you pushed it a little bit up, you pushed it a little bit down, and this is what you obtain. But it always have to be formed quasi-statically in equilibrium. Always. Okay, so for any t, p is always a decreasing function of p, and it's a continuous function. There is no jumps. This is a bad model.
נגיד שעובר מגז לנוזל, אז מה, הכל מיד עובר זה יחד?
Yes. You've seen the bubbles? The bubbles are a small portion of water that's instantaneously turned into vapor. Like that. Okay. So in order to correct this, and people already have known that this is a bad model, there came a guy named van der Waals. Okay. And he invented a different description. Okay. He said, well, clearly this stuff does not work. It does not show me any phase transition, and experimentally it was a little bit off, at least for low enough temperatures. Okay. So what have van der Waals have done? He was a clever guy, so he said, I don't know how exactly to obtain this equation. This equation is a quasi-statically, and I shifted a little bit down or up, right? This is the usual description. And here are gas molecules, and you applied some weight over here. And this is how you derive the ideal gas equation. Van der Waals said the following thing. Look, I'm starting with P, V equals nRT, okay? And I'm going to modify it. How I'm going to modify it? I'm going to modify it in such a way that eventually I will get some sort of a phase transition. Okay. So first of all, he said, look, this part over here, we will decrease it a little bit. Let's assume, and they already had those thoughts, that there are molecules. So the volume, the total volume, we have to decrease from this volume the self-volume of the molecules. Right? We're looking on the volume of the gas. Okay? But each dot over here has some sort of a specific volume. It's not a continuous media. There are some molecules inside, some atoms. So we will decrease V by number of moles or number of molecules that we have inside, minus a specific self-volume of each molecule. Great. This is still not enough. And then he said, well, if there are molecules, then the pressure also has to be modified. How is going to be modified? So the total volume is increased by the self-volume of the molecules, but the total pressure is decreased by the presence of the molecules because they have interactions. Okay? They not simply push each other, right, like billiard balls. They somehow interact and maybe pull each other a little bit. And this, he put an equality sign over here. He said this is the van der Waals equation. And the nice thing about this van der Waals equation, and this is what we will see on Tuesday, is A, it's producing very nice phase transitions that you can study, and it's a very simple model for phase transitions. B, it actually satisfies what happens to gases when they transit from gaseous state into sometimes solid state and sometimes vapor, liquid state for a very wide range of temperatures. So this equation, the van der Waals equation, is much more valid and much more true description of the nature than this simple ideal gas. How exactly he got it? He simply guessed. Right? Simply guessed. All right, see you on Tuesday. Okay. הוא אומר, את הווליום צריך להגדיל. ואז כדי שהנפח האמיתי הוא נפח יותר גדול, צריך להוריד ממנו את הנפח של המולקות עצמן. ואת הלחץ צריך להוריד קצת, כי